So now let's move on to position time graphs. This looks familiar before. This was our motion diagram showing a dude on a skateboard rolling along at constant speed. And remember, we start with time zero, and the assumption here is that these are regular time intervals as he's rolling along. Now, this is our position time graph, a simplified version of one. And P is the position, that's on the vertical axis, and the time is on the horizontal axis. Now, the graph for this individual here, we're going to call this position 0, so that's where he is, and he's going to go to position 3, which is up here. But as he rolls along, some time is going to pass, some period of time is going to pass. So let's do this, and we'll use this line. This will be good. So as time passes, he's making his way down the course from position 0 to position 1, 2, and 3. Now, if he goes at this speed, this is what it looks like. Now, what if he goes slower? What if he slows down? Well, it's going to take him longer, more time to get to the same position here. And if he goes faster, well, it's going to take him less time. So what you can see is the slope of this line, the slope of the position versus time graph, is an indication of his velocity, right? A steep line is a fast, high velocity. He gets there in a hurry. While a flatter line, more time to get there, means a slower velocity. Now, why does this work? So this is position, this is time, this is our graph here, okay? Now, how do we calculate the slope of a graph? From your math class, from way, way back. How do you calculate the slope of a line on a graph? And it is the rise, slope, equals the rise over the run, as you recall. So the vertical axis here is position, and the units of position normally is meters, and the y-axis, or I'm sorry, the x-axis is time, and the unit of time is seconds. So if we take the slope of this thing, we want the rise over the run, which is going to be meters divided by seconds, meters divided by seconds, meters per seconds. That is velocity. Isn't that interesting? When Isaac Newton figured this stuff out, and he defined velocity as, distance per unit time, this was just shorthand for the graph. It was a shorthand for the slope of the graph. Velocity literally means the slope of a position versus time graph. And the steeper that slope is, the faster the thing is going. Okay? What if we're going backwards? I think I can do it on this one here. What if, let's do this. We'll just flip this thing around. There we go. He's going backwards. He starts at position 0, and he goes to -3. Now our graph has a negative slope. So he has a negative velocity. He's going backwards. And if it's a steep negative slope, he's going backwards really, really fast. Okay. So the stuff we've told you about velocity having positive and negative, and the sign indicates the direction. Really what the sign indicates is the slope of the position versus time graph. Okay. All right, let's see. So slope of position time is velocity. Now let me show you another one that you might find interesting, and that is velocity versus time. This is also a very useful one. So our skateboarder was going at constant velocity, but our runner, our sprinter, she's going faster and faster as she moves to the right. And the car, conversely, is going slower and slower as it moves to the right. Now, what is her graph going to look like? So this time, rather than position versus time, we're doing velocity versus time. If you did plot this on a position versus time graph, you'd get a kind of a curve where it would get steeper and steeper and steeper. She doesn't go very far in the first second, but she goes farther in the second and even farther in the third. So it would be an upwardly curving graph, meaning that it's getting steeper and steeper all the time, meaning the velocity is getting higher and higher. So if we just graph her velocity versus time, skip the intermediate step there. Let's do this again. Let's do that. She starts off from the starting line at position 0, time 0, and as she runs along, she's going faster and faster. Her velocity is getting higher and higher. The spots are getting farther and farther apart. Now, the car, which is slowing down, that is beginning at a fast rate and slowing down and stopping. So starts off fast, slows down, and stops. Yes, anyway. Now, what does the slope here represent? What does the slope of a velocity versus time graph represent? I'm going to let you think about it here for a moment. Pause it if you want to scratch your head a little bit. But the question is, what does the slope of a velocity versus time graph represent? I'll give the answer here in 3, 2, 1. The answer is acceleration. The slope of a velocity versus time graph is acceleration. Okay. Now, how does that work out on the paper? Let's look at this. So, slope of v versus t equals acceleration. That's supposed to be a t. Okay, so we have velocity versus time, and our units of velocity are meters per second, and our units of time, again, are seconds, just like they were up here before on the position versus time graph. And again, we're going to calculate the slope, and the slope is the rise over the run. So that's the rise, and that's the run. So that is equal to meters per second. That's the units of the vertical axis, divided by seconds. And when we multiply them across, we get meters per second squared, which you should recognize as the units of acceleration. So again, when Newton figured this stuff out and defined acceleration described as meters per second squared, what he was literally doing was describing the slope of a graph of velocity versus time. Okay. Now, we're going to see next time that we manipulate these graphs and we pull information off of these graphs to actually be able to hang numbers on these things, not just slopes. And these equations that we use are shortcuts for analyzing graphs. And the next one is, again, a velocity versus time graph. And that is to look at the area under the graph. So here, this line here, this describes a, like maybe the skateboarder that we started with beginning, velocity time graph. If he's rolling along at 2 meters per second and never speeds up and never slows down, then his velocity time graph is just going to be a level straight line, never going faster, never going slower as time passes. So if he goes along for 2 meters per second for 5 seconds, 2 meters per second for 5 seconds, how far has he gone? Velocity is delta x over delta t, right? And so in this case, 2 meters per second is equal to some distance divided by 5 seconds. And to resolve this, we need to multiply both sides by 5 seconds times 5 seconds. These cancel. The seconds cancel, and we get 10 meters is equal to the distance that we went. Okay, that's the distance that we went. All right, well, let's look at a curious thing here back on our original graph. This is 5 seconds, so imagine there's 5 lines here, 5 vertical lines going up to 5 seconds. Probably should have put that on there. And 2 marks going up to 2 seconds. How many squares would there be underneath this graph? What is the area of this region? And it is 2 times 5 is 10. So the area underneath a velocity time graph is the displacement. It's how far we went. Let me show you that on the clipboard here. Okay, so we have our velocity versus time. This is meters per second. This is seconds. And we have some area underneath it here, right? Now this area is the base times the height. It's a rectangle, base times height, which in this case, I'm going to kind of switch these around here a little bit, is meters per second. That's the vertical times the horizontal, which is seconds. And when you multiply those together, the seconds cancel and it gives you meters. So it turns out that the area underneath a velocity versus time curve is the displacement. We can use the area on the graph by counting the squares to figure out how far we went. Okay, let me show you another example here. What if we had another skateboarder who started at 3 meters per second and slowed down and stopped? Okay, so they started at 3 meters per second and slowed down and stopped. What does that look like? 4 seconds, or maybe even a little less than that? So we're comparing somebody who goes 2 meters per second for 5 seconds to somebody that goes 3 meters per second but slows down and stops in 4 seconds. Who went farther? Well, we could do the math, but we can also just look at the area underneath this curve. And I think it's painfully obvious that the area of this rectangle is significantly greater than the area of this triangle here. There's only a little bit poking out here. This area is much smaller than this one. So clearly the person that was going 2 meters per second and never stopped went farther than the person who was going slow and slowed down and stopped, right? AP College Board wants you to know this. They want you to be able to just look at two graphs, compare them, and be able to pull information off them like that without doing any math. You're just kind of recognize it. Let me show you one more thing. Suppose we start at, let's start at, 1.5 meters per second. Trying to make this even here. There we go, about 1.5 meters per second. That's probably about right. Start at 1.5 meters per second and go one direction, slow down, stop, and then go back the way we came. Think of this like you throw a ball straight up from your hand, like you're juggling, and you throw the ball straight up, and then it comes down, you catch it again. It goes up and you catch it. It's going fast upward, it's going slower, stops at the top, and then falls faster, and lands in your hand. Well, how far did it go net during that trip? What is its total displacement at the end of that entire trip? Common sense tells us it didn't go anywhere. It left our hand and it landed in our hand. Let me put my hand where you can see it. There we go. It left our hand and it comes back in our hand, so it didn't go anywhere during the round trip. And we can see it in the graph too, because the area under the curve going upward is the same as the area under the curve going downward. When I say under the curve, really what I mean is between the graph and the zero line, the origin. Okay, so since this area is the same as this area, it returned to its starting position. That's another thing that AP wants you to be able to do, and it's really useful. It makes you feel smart, because sometimes they'll throw numbers at you on a graph and you can just make qualitative distinctions between, hey, this is more than this. What if he slowed down, went back the way he came a little bit, but wasn't going as fast at the start? Well, clearly he's going to have gone net forward, even though he backed up a little bit. Okay, let's put this back here and this over here. So that is velocity versus time graphs. The area under the velocity versus time graph is displacement. The slope of velocity versus time is acceleration, as we said before. And then finally, position versus time, the slope is velocity. Now you may be wondering, well, what is the area underneath a position versus time graph? Well, you can do the math on that, but it turns out it's meaningless. Okay, if you need more evidence that physics is not math, if physics was math, then anything that you could do in math would have meaning in physics. And calculating the area underneath a position versus time graph is a number, but it's a meaningless number. Anyway, I digress. Let's move forward here. Okay, we're getting close to the end here.